cyclic group. What is a cyclic group? Read the definition. There are some groups which can be generated by single elements. Yes or no? So there are some groups, cyclic group. This is a group which can be generated by a single element. A single element can generate this group. Another definition is what? Group with at least one generator. Yes or no? So both the definitions are same. Group that can be generated by a single element. So if you have a group which can be generated by a single element, then that element is generator. So I can say group with at least one generator, that is called cyclic group. Very simple definition. For example, 1, 3, 5, 7, multiplication modulo 8. Do we have is this a cyclic group? Tell me. Is this a cyclic group? Can I say this is a cyclic group? The answer is no. This is not a cyclic group because you can notice there is no generator here. In this group, if you notice, there is no generator. If you notice the what 1 can generate, that can generate 1. What 3 can generate, it can generate 1, 3. What 7 can generate, it can generate 1, 7. Okay, and similarly what 5 can generate, order of 5, that will be 2. Order of 3, that will be 2. Order of 7, that will be 2. Correct? Because 7 can generate only 7 power 1, 7 power 2. What is 7 power 2? What is 7 power 2? That is 1. Okay, so that is the idea. Because 7 power 2 is 1, so order of 7 is 1. Because 5 power 2 is 1, which is identity element, so order of 5 is 2. So you can notice there is no generator. In this, there is no generator. I can say this group cannot be generated by a single element. Can I say yes or no? There is no generator. So this is not a cyclic group because there is no single element which can generate this. So this group is not cyclic because you cannot generate this group by a single element. Now consider this group. Okay, let's check it out. Is this a cyclic group? So can I say which element will generate this complete group? Which element has the power to generate this complete group? See, identity element cannot generate this whole group. What 2 can generate? What is the order of 2? Find the order of 2. Order of 2 means smallest power. What is the smallest power that will give me identity element? What is the smallest power? The minimum value is 4. The minimum value is 4, for which I will get 1. Okay, so because you can notice 2 power 4, that is basically 16 mod 5, and that will be 1. And what is 2 power 3? 2 power 3 will be 8 mod 5, and that will be 3. So you can notice this will be 3, and finally you will get 1. So I can say 2 is the generator. This 2 can generate everything. Order of 2 is 4. The smallest value such that you will get 1. The smallest integer, the smallest positive integer is 4. So I can say this 2 is the generator. So this 2 is your generator. And what is inverse of 2? You don't have to go anywhere. This is your inverse of 2. You don't have to calculate again. This is your inverse of 2. So 2 inverse is 3. So I can say this 3 is also generator. 2, 3. These are the generator. So this is a cyclic group. Can I say this is a cyclic group? Yes, this is a cyclic group. So cyclic group is a group which can be generated by a single element. Okay, the definition is very simple. So for example, in this group, what is the generator? Is this a cyclic group? 1 minus 1 iota minus iota. Yes, this is a cyclic group because iota is the generator. So this can be generated by I. This group can be generated by iota. This group can be generated by minus iota. So iota comma minus iota, these are the generator. There can be more than one generator. For example, this group you notice, this your Zn. Can I say this Zn, comma, okay, is this a cyclic group for all n? Can I say this is a cyclic group for all n? In this, your generator. Can I say this is cyclic group for all n? Can I say? Cyclic group means, do we have a generator? Basically, do we have a generator? Is there any generator in this Zn, comma, addition modulo n? Yes, the generator. One generator is 1, right? The generator is 1. So generator is 1 if and only if I can say this one of the generator is 1 if and only if n is greater than or equal to 2. If you have Z1, is this a cyclic group? This is your Z1. Tell me, is this a cyclic group? Only single element you have. Yes, this is cyclic because this zero itself is the generator. So yes, this is cyclic. This zero itself will be the generator. I can say the generator will be 0 for this situation, for this Z1. And for this Z2, the generator will be 1. This is also cyclic and the generator will be 1. Okay, is this clear to everyone? So whatever value of n you take, this is always cyclic. For all n greater than equal to 2, at least one generator you have. This at least one generator you have. Okay. So this is the definition of cyclic group. So very different. Cyclic group means every element can be generated by a single element. So you can notice this Z is cyclic. What is the operation? The operation is not given. So tell me, when I am talking about integers, which operation I am talking about? What is the operation here? So for integers, this addition is the operation. And for this addition modulo n is the operation. And you can notice they are generated by 1. 1 is the generator for both of them. So they are cyclic because this one can generate. And what about this? Group of nth roots of unity. Is this a cyclic group? Nth roots of unity. For example, this group you have. This is one root of unity. This is second root of unity. This is third root of unity. This is fourth root of unity. And so on. So, is this a cyclic group? Yes. What is the generator? Just tell me the generator G. Generator G is 1. And what is the generator here? What is the generator here? That will be again, the generator here will be 1. Sorry, minus 1. The generator will not be 1. Here the generator will not be 1. Because this is your nth roots of unity. What is the operation? What is the operation? What is the operation? Operation is multiplication. Okay, operation, you already know operation is multiplication. So here generator is 1. And here what is the generator? Omega comma omega square. These are the generator. And here what is the generator? Iota comma minus iota. These are the generator. So can I say all of them are? Yes. Similarly, you can check nth roots of unity is a cyclic group. Because remember, every cyclic group, if you note, can I say every cyclic group can be written like this? If you have cyclic group, what it means? Just very simple thing. Cyclic group means what? There exists a generator. Means there exists a generator. There exists a generator G. Agree? Cyclic group means there exists a generator G. So I can say if you have a cyclic group G, so if you have a cyclic group G, then how can I write it? And for which generator is G, then I can write the G is equal to what? Tell me what G is equal to what? G is equal to this, yes or no? Because you have a generator G. G is the generator, means G can generate all the elements. G can generate all the elements, agree or not? So G can generate all the elements. So I can say G power 0, G power plus minus 1, G power plus minus 2, G power plus minus 3, and so on. So every element can be generated by G. This is how you can write. Every cyclic group you can write like this. So remember, this is the definition. Every cyclic group, if you have a cyclic group G, then it will look like this. Because every element can be generated by this generator. Every element you can generate by this generator. This is how this cyclic group will look. Okay, is this clear? Now you can notice nth roots of unity, how that looks. Nth roots of unity, I told you this looks like this. 1 comma theta square comma theta power 3 and so on theta power n minus 1. So can you notice this is a cyclic group? This is the structure of cyclic group, yes or no? So this is your cyclic group. And what is the identity? What is the generator? What is the generator? So this theta is your generator. Okay. So nth roots of unity we have already seen. Basically, whatever nth root of unity you take, this you take, or this you take, or this is the third root of unity, this is fourth root of unity, whatever you take, it is always a cyclic group. So the answer is yes. Is this a cyclic group? The answer is yes. This is always a cyclic group. And what about this Zn? Is this a cyclic group? This also we have seen yes. Okay, we have already seen that this is also yes, because you can write this Z10 actually, remember, because this is a cyclic group, this Z9 is cyclic group. So actually you can think like this. This is basically, you can think as 1 power 0, 1 power 1, 1 power 2, 1 power 3, and so on, 1 power 8. Like this you can think. And this is the structure of cyclic group. Yes or no? Because 1 is the generator, so I can write like this. So I can say this is a cyclic group because you have a generator. There exists a generator. This is how you can write. And this is your 0, 1, and so on 8. So you can notice both these things are same. What about UN? Can I say every UN is cyclic? Can I say every UN is cyclic? The operation you already know, multiplication modulo n. This is the operation. You already know the operation. And here also you know the operation. Operation is addition modulo n. So tell me, can I say every UN is cyclic? The answer is no. The answer is no. Because you can notice this is not cyclic. Like 1, 2, 3, 4. This is cyclic. You can notice this is your U5 and this is cyclic. But if you notice U8, this is not cyclic. We have already seen. Okay. So this is the question. Is this cyclic group? This is the question. Z7 star. This is non-zero elements of Z7 and the operation. Basically, what is this Z7 star? In this question, basically this, what is this? In this question, from the description, this is actually U7. Very good. This is actually U7 because operation is also multiplication modulo. Okay, 7. You can notice the operation also. Operation is multiplication modulo 7. So from this question, this Z7 plus this is nothing but U7. And is this cyclic? Yes, this is a cyclic. You can notice this is cyclic, and you can check the identity element. The generator. What will be the generator? Think about it and tell me, what will be the generator? Which element has the power to generate all the elements? You have U7. U7 is 1, 2, 3, 4, 5, 6, 6. This is your U7. So what are the generators? Identity element can never be the generator because identity element can only generate itself. So identity element will never be the generator. Okay, let's find out order of 2. What is the smallest value such that you will get identity element? What is the smallest value? Like 2 power 1, 2 power 2. What is 2 power 2? That is 4. 2 power 3. That is, yes. So that will be, I can say n equal to 3. So I can say order of 2 is a 3. So can I say what is 2? Can I say 2 is generator? So 2 is not generator, right? Because 2 can only generate 3 elements. So 2 is not generator. 2 is not a generator because 2 can only generate 3 elements. See, 2 can generate 2 power 1, 2 power 2, 2 power 2, and 2 power 3. So 2 power 3 will be the identity element. So you can notice. So this is the only these elements can be generated by 2. And you can notice 2 inverse is also 4. So order of 4 is also 3. So I can say order of 4 is also 3. So this 4 is also not a generator. So 2, 4, these are not generator. What about 3? What is the smallest value? What is the smallest value such that you will get 1? Tell me, what is the smallest positive value? What is the smallest positive integer that will give you 1? You have mod 7. So 3 power 1, 3 power 2, 3 power 2, 3 power 3, 3 power 4, 3 power 5. So what is 3 power 5? What is 3 power 5? 3 power 5 is this mode 7. You also have to take mode 7. Don't forget to take mode 7. So if you take mode 7, what you will get? Okay, so we will get 5. So what will be 3 power 6? That will be 3 power 5 multiplied by 3. 3 power 5 is 5. So 5, okay, so that will be 15 mod 7. And that will be 1. So right. So order of 3 is actually 6. Order of 3 is actually 6. The smallest value. So the 6 elements, and you can notice only 6 elements. So order of 3 is 6. It means what? It means what? Tell me, it means what? It means 3 is the generator. It means 3 is the generator because 3 can generate everything. Because order of 3 is 6. It means 3 can generate all the 6 elements. This 3 can generate all the 6 elements. Yes or no? And what is 3 inverse? 3 inverse, what is that? So that will be 5. 3 inverse is 5. So in this example, 3 inverse is 5. So 3, 5, both are generator. And what is the order of 6? What will be the order of 6? So that will be, I think, that will be 2, right? Because you can notice 6 power 2. What is 6 power 2? So that will be 36 mod 7. So that will be 1. So I can say, okay, so 6, order of 6 will be 2. So finally, I can say that 5, 3, these are the generators. 3, 5 are generators. And you can notice order of 6 is 2 because 6 power 2 is 36 mod 7 and that will be 1. So I can say this is not a generator. So the only generator are 3, 5. Let's assume you have some finite group. Okay, so you have some finite group. Let's assume G. Okay, and let's assume order of G is n. Then what can you say about A power n? Then what can you say about A power n? For all A, what can you say about A power n? For example, okay, with example, you try to understand. Like in this example, this U7 example you take. This U7 example, 1, 2, 3, 4, 5, 6. This U7 example you take. And tell me, what is 1 power 7? Tell me, what is, basically I'm asking if you can notice the order here. Sorry, the order is 6, right? The order of U7 is actually 6. So what is 1 power 6? Because the order is 6. Remember, the order of U7 is 6. So what is 1 power 6? That will be 1. Only identity element. What will be 2 power 6? What will be 2 power 6 in this? That is also 1. Just check it out. 2 power 6 is also 1. 3 power 6. Just check it out. This is also 1. 4 power 6. That is also 1. 5 power 6. That is also 1. 6 power 6. That is also 1. Can you see what I'm trying to say? This we will prove after some time. At the end, we will see this. This at the end. This is the application of Lagrange theorem. So if you have any finite group whose order is n, then for all A, this will be identity element. Okay. So for all A power n will always be identity element. It will always be identity element. For all A, whatever element you take, A power n is always identity element. Like in this you can notice that whatever element you take, 4 power 6 is always 1 in this group. But the generators are what? The generators are 3, 5. Only these are the generators. Nothing else is a generator in this group. So this is a cyclic group. So I can say U7 is a cyclic group. But remember, whatever group you take, any finite group you take. So for any finite group, this will always happen. This will always happen that any element power n, that will always be identity element. Okay, so you can just take it as a note maybe. But anyway, this we will see in the Lagrange theorem. Okay, let's see one interesting thing. Can I say every cyclic group is abelian? Can I say every cyclic group is abelian? Very easy this is actually. If you see, every cyclic group is abelian. Can I say every cyclic group is abelian? Can you prove it? The answer is yes, but can you prove it? Just apply the definition. Cyclic group means what? One by one, you will tell me. One by one, I am asking. Cyclic group means what? Tell me means what? Means there exists a generator. Cyclic group means there exists a generator. There exists a generator G. Okay. So can I say that if you have a cyclic group G, then G I can write like this. I can write G as like this, because every this is generator. So every element can be generated by G. You can generate every element by G. So I can say cyclic group I can write like this, correct? 0 power 1, G power 2, G power 3, and so on. G power minus 1, G power minus 2, and so on. Agree? Right? Yes or no? So this is the point. So any cyclic group, this is the template of cyclic group. Remember, any cyclic group can always be written like this. If you have a cyclic group, then you can write as 0 power n, where n is an integer. This is how you can write. So this is how you can write the cyclic group. Remember this. Any proof, if you ever see cyclic group, this word if you ever see, always remember that cyclic group is basically nothing but G power n, where G is the generator. So this G is equal to, this group is equal to G power n, where n is integer. Now tell me, now if you take any two elements from this group, what are these two elements? Tell me. Can I write them as G power m, G power n? Can I write them as G power m, G power p, something like this? Can I write? Yes or no? Any two elements you take, you can write them G power m, G power p. You can write like this. And now tell me, so can I say AB equal to BA? Very simple. See, the proof is very simple. Can I say AB equal to BA? What is A? A is G power m. What is B? B G power p. Can I say this is equal to G power p, G power m? Yes, of course. This is G power p plus m. This is G power p plus m. So they are same. Cyclic group. Cyclic group means you have a generator. There exists a generator. So this cyclic group you can write like this: 0 power G power 0, G power 1, G power 2. So this cyclic group you can write like this. Every cyclic group you can write like this, where this G is the generator. This G is the generator. And now you can notice, whatever two elements you will take, A comma B, any two elements you take, they are nothing but G power m, G power p. Agree? So I can say that, can I say AB equal to BA? Yes. Because you can notice, this is also G power p plus m. This is also G power p plus m. So what can I say? So every cyclic group is abelian. So every cyclic group is abelian. Can I say every abelian group is cyclic? Can I say every abelian group is cyclic? Can I say every abelian group is cyclic? The answer is no. But give me a counter example. Give me a group which is abelian but not cyclic. Yes, very good. U8. You can take this U8. This U8 you can take. Multiplication modulo 8. This group you can take. 1357. Multiplication modulo 8. This group is abelian. Why this group is abelian? Anyone? Anyone want to tell me why this group is abelian? Because this is group of order 4. Abelian, this is abelian, right? Yes, this is multiplication, so this is commutative. Multiplication is commutative, very good. But this is also group of order 4. This is a group of order 4. So of course it is abelian. Every group of order 4 is abelian. We have already seen. And you can notice this is not cyclic. There is no generator. One more question. What is the order of smallest group which is cyclic, which is not cyclic but abelian? Order of smallest group that is not cyclic. What that will be? Answer will be 4. Because you can just check it out. Every group of order 1. See, order 1 group will be cyclic. If you notice order 1 group, that will be cyclic. Order 2 group also will be cyclic. Order 3 group, that also will be cyclic. Can you check order 3 group? Only one order 3 group you can create. Only one order 3 group you can create. What is this? So this will be B, E. So it will be E, it will be A, right? This is the only possibility. This is the only possibility. Is this cyclic? Is this, what is the generator here? Is this cyclic? Just tell me, is this cyclic? Can I say this is cyclic? Just check it out. What is the generator? Let's check. A power 1, that is A. A power 2. A power 2 is B. And A power 3. A power 3 means what? A power 2 is B. See. A power 1 is A. A power 2 means A into A, that is B. And what is A power 3? A power 3 means A into B. Because A power 3 means A square A. A square is B. So that is BA. And BA is E. So yes, A can generate all the elements. So this is cyclic because A can generate all the elements. So what are the generator here? What are the generator? A is the generator, also B is the generator. You can just check it out. So the small order of smallest group that is not cyclic, the answer will be 4. Every group of order less than 4, every group of order 1, order 2, order 3, they are cyclic. You can notice this is order 3 group and this is cyclic. So similarly, they can ask you this. What is the order of smallest group which is not cyclic but abelian? Now what will be the answer? Now again answer will be 4. The answer will be same. Answer will be 4. So every cyclic group is abelian. The proof is very simple. Because every 2 elements in a cyclic group, every 2 elements will be like this. Because G is the generator. If G is the generator, then every element can be generated by G. So every element looks like this. So I can say yes, it is a cyclic. It is abelian. Every cyclic group is abelian. This is the question. GATE 2009 question. Tell me quickly what is the answer. GATE 2009. Which one of the following choices is correct? Which is generator? Consider the table, composition table of cyclic group. This is a cyclic group and you have to find the generator. First you tell me which can never be the generator. First you tell me which element can never be the generator. Identity element can never be the generator, right? So what is the identity element here? This is ABCD. This is ABCD. So A is the identity element. You can notice that identity element is A. And identity element can never be the generator. Can never be the generator. If identity element is the generator, then what will happen? This is my question. If identity element is the generator, then what is the group? If identity element is the generator, then group G is order of G will be 1. G will be simply this trivial group, this cute group. Okay, so in this situation, G will be trivial group. Okay, only in the trivial group, G can be the generator. In other situations, G cannot be the generator. So you can notice, sorry, this identity element cannot be the generator. So this A is not the generator. So you can say this is not correct. This is not correct because A cannot be the generator. A is the identity element. Now let's check. What can you think? What do you think about B? What is b power 1? B power 1 is b. What is b power 2? B power 2 means bb. bb, and bb is a. And a is the identity element. And a is the identity element. So what is the order of b? Because b square is e. B square is e. So what is order of b? Order of b is 2. So b is not. So I can say b is not generator. So b is also not generator. Okay, let's think about c. What do you think about c? C power 1 is c. C power 2, that means cc. That is b. And what is c power 3? That means c square c. So that is bc. What is bc? bc is a d. And what is c power 4? That is c square c square. So that is bb. And what is bb? That is a. And that is identity element. That is identity element. Yes, correct. So c is the generator and d is the generator, because c inverse is a d. C inverse is d. Okay, so yes, so I can say c comma d is the generator. Any doubt in this? Which template is this? Can you notice which template is this? Group of order 4. Group of order 4. Which template is this? If you notice, this previous template was like this. You have identity element, there is x which is inverse of itself, and the remaining two are inverse of each other. The remaining two are inverse of each other. And here, this is cyclic. This is cyclic group. This is cyclic group. And let me tell you, and what are the generators? What are the generators? The generators are y comma z. These are the generators. Is this clear? This is your template. Only two templates are there for order 5 or order 4. Only two templates you have. And this template, what is this template? This template is this. What is the another template? The another template is not cyclic. The another template is not cyclic. This another template, where for all elements, A inverse is A. Okay, in this template, this is not cyclic. There is no generator. Very simple question. A is the identity element here. First of all, you find identity element. A is the identity element. Now you can notice B square equal to E. It means order of B is 2. So B can only generate 2 elements. Order of B is 2. It means B can generate. It means B can generate only 2 elements. But C comma D, they are inverse of each other. So this template, this is the fixed template. One thing you tell me, for this question, like in the GATE exam, if you see a order 4, then now will you solve that question? In the GATE exam, if you see order 4 group, order 4 group, order 3 group, order 2 group, order 1 group, will you solve that question? No, don't solve that question. Just check the template. Order 1, 2, 3, 4. The templates you remember, that's it. You don't have to remember the templates for order 5, order 6. You don't have to remember. But the order till order 4, all the templates, everything we remember, everything we know.